So I was going to start talking about kind of domain and range of functions of two variables. So let's look at some, actually, before we even do that, let's kind of remind ourselves of how domain and range work in general. So let's say, well, let's write down where we're at, Co-16C. Today is the 19th of April. Domain and range. As usual, if you have questions, don't hesitate to ask. I say lots of things. I'm always happy to clarify. So let's look at back something like from like 16a. Let's say we want to find the domain and range of the following function. Let's say we had f of x equal to the square root of x minus 3. If I want to find the domain, well, when you're looking for domain, there's three typical things we look for. We don't want to have division by 0. We don't want to be taking the square root of a negative number. I think don't. I really should be saying we can't, right? We can't divide by 0. We can't take the square root of a negative number and get a real result. And we can't take the logarithm of a 0 or a negative number. So here, if I see this function here, I know that the domain is going to be, I have to set x minus 3 to be greater than or equal to 0. Because I can't take the square root of anything negative. So here, I'm going to get x greater than or equal to 3. Which I would write as the interval notation, everything from 3 to infinity. The range, on the other hand, unfortunately, is usually a little harder to manage. In 16a, we probably talked about finding like the inverse function and then maybe finding the domain of that. And sometimes that's an option, sometimes it's not. In this class, it's really not an option to find the inverse function. What we typically have to do is kind of think about what the graph might look like. Now, we're not actually going to graph it. We're just going to ask ourselves, okay, well, for the range, I should say, here's the domain. For the range, we know that x has to be greater than or equal to 3. What values do we get for the function f of x equal to the square root of x minus 3? And I try to think about kind of the ways this can be as small as possible and the ways this can be as big as possible. So I can see that if x equals 3, then f of 3 is the square root of 3 minus 3, which is the square root of 0, which is 0. And that's the smallest this can ever be, right? Whenever you take a square root specifically, it always has to give you a non-negative result. But then, this can be as large as we want it to be. This function, square root of x minus 3, can be as large as desired. It might help to graph the thing, right? Like, even though I'm writing all these words, if I just think about the graph of this for a second, it's your usual square root graph shifted 3 to the right. So starting over here at x equal to 3, it's just doing the usual square root thing, which looks kind of like that. And even though it kind of, it has this kind of shape to it, it's never like turning around and going down, or even leveling out towards a horizontal asymptote. It keeps on getting larger and larger and larger and larger. So we can see that there is no upper bound on the range. The range here starts as low as 0 and is infinitely large. If you have to justify this to yourself, you can say, well, for example, is there a way I could get the range to have a value of 1 billion? Yeah, I can get 1 billion. A lot of zeros. Set the function equal to 1 billion and solve for x. If I set the square root of x minus 3 equal to 1 billion, I can definitely find an x value that's going to make that work. If I square both sides, I get 1 billion squared, and then add 3, x would have to be 1 billion squared plus 3. And that would give me an output of 1 billion. And you could have made that number as large as you wanted. And you could always find an x value that will give you that value. It won't work when we pick a negative number though, right? There's no, like if I set this equal to -2, there is no number I can plug in that gives me a value output that's -2. The square roots always give us positive. Non-negative, you get 0 outputs. Questions so far? Okay, let's talk about a similar-ish but different example. Let's say that I wanted to find the domain. Number one, trying to number things, but I'm not always good at it. The domain and range of something like, f of x comma y, so a function of two variables equal to the square root of 9 minus x squared minus y squared. It might help to graph this thing. All right, let's go ahead and graph it. Let's actually talk about how we would graph this thing. So I'm going to find the traces. When someone says the word traces, you should be thinking what's happening in each of the three coordinate planes. So in the xy plane, well, if I set z equal to 0, so z is the stand-in for our function, right? This f of xy, we are usually thinking of as that's our z. If we set z equal to 0, we're going to get 0 equal to the square root of 9 minus x squared minus y squared. That might not look very promising, but if we do a little bit of algebra, we can see something a little more useful. If I square both sides, I get 0 equal to 9 minus x squared minus y squared. And if I add x squared and y squared to the left-hand side, I get x squared plus y squared equal to 9. That's a circle of radius 3. So in the xy plane, we're getting a circle of radius 3. It was already in the function. So we started off with the square root of 9 minus x squared minus y squared. Yeah, just an example function. Let's find the other traces. So I will point out, kind of like in the examples we were doing on Monday, there's some symmetry here. Here, you can kind of see that if you interchange x and y, you'd still have the same function, right? If I replaced x with y and y with x, it wouldn't look any different. When that's the case, kind of like last time we were talking about like the hyperboloid of one sheet and the hyperboloid of two sheets, you could have interchanged x and y and still have the same thing. When that's true, it usually means you have some symmetry around the z-axis. It also means your traces in the xz and yz planes are going to look the same. Let me show you what I mean. If I look at the xz plane, well, that's going to be where I set y equal to 0, and I'm going to get z equal to the square root of 9 minus x squared. So what does that look like? Well, we don't want to keep having to square both sides to figure it out. I'm going to tell you that's the top half of a circle of radius 3. We can certainly see that z has to be positive because it's the square root of something. But if we did square both sides, you'd have z squared equal to 9 minus x squared, or x squared plus z squared equal to 9. The difference here is that this doesn't give you the full circle of radius 3 because z had to start off being positive. Whereas here, x and y could have been positive or negative. And then in a very, very similar way, in the yz plane, we get the same looking shape. We have x equal to 0. We have z equal to the square root of 9 minus y squared. And we're going to get the exact same top half of a circle of radius 3. So now if I try to put this all in my x, y, z three-dimensional coordinate system, when I'm graphing something in 3 dimensions, I usually try and see what's happening in the YZ plane first, because that's like the plane that's on the piece of paper, and it's usually the easiest for me to try and draw. So in the YZ plane, I've just got that semicircle of radius 3. And then in the XZ plane, same deal. Actually, let's do XY plane next. So in the XY plane, I've just got the circle of radius 3. And if I really need to, I can draw what's happening in the XZ plane, which is just that we've got this circle, this semicircle as well. Like that. So there's our semi-sphere or hemisphere is the correct word, or hemisphere of radius 3. We can definitely talk about what the domain and the range are. The domain here, domain's a little different than it was before. The domain isn't just all the x values, it's all the xy coordinates. Sorry, xy coordinates. So unlike way back when, we're not going to write the domain as an interval. We're going to describe the domain as a region in 2 dimensions. So here, the domain is all points inside the circle of radius 3. Center is the origin. It's a lot of writing. Here's the more mathy way of writing this answer. It is the set of all points x comma y such that x squared plus y squared is less than or equal to 9. Which I really should have gotten by actually finding the domain in the usual way. But if I actually look at my function here and say, what's the domain? I'm just going to take the insides of that, just like I did in my previous example, and say, well, the insides of the square root have to be greater than or equal to 0. And if I bring the x squared plus y squared over to the other side, I get 9 is bigger than or equal to x squared plus y squared, or x squared plus y squared is less than or equal to 9. I didn't show that work at first because I had already seen the circle that I knew I had to be inside of, but that's really where that's coming from, is that we are saying our domain is every single point in this circle here. We can't pick any point outside of it, right? If you pick this point over here, like the point 0, 4, 0, that's not a point on our surface. If I plug in 4 for y and 0 for x, this inside is going to be negative, and it's not going to be in the domain. Questions or comments or thoughts? So again, for these functions of 2 variables, the domain is an area in 2 dimensions, not just a line on the real number line or an interval on the real number line. The range, on the other hand, is still an interval because the range is just all the output values. So if we look at this hemisphere here, what's the lowest z value I get on that hemisphere? How low can we go? Yeah, you're right, Josh. 0. The range, we're definitely as low as 0. So, and what's the highest z value we get right there? Well, if x and y are both 0, which is what that looks like it is, 9 minus 0 is 9, and the square root of 9 is 3. So the range here really is an interval. The range is bracket 0 to bracket 3. I can't go any lower than 0 because it's a square root, or it's only giving me non-negative results. And I can't go any higher than 3 because there's no way to make this number any higher than 3. The way I would view that, if you want, like if you weren't drawing the graph, I would say, look, I've got the square root of 9 minus x squared plus y squared. And I know that x squared plus y squared is always greater than or equal to 0. So this thing here is always bigger than or equal to 0. If I want to make this whole thing as large as possible, I'm going to make the thing I'm subtracting off as small as possible. The smallest it can be is 0. 9 minus 0, the biggest that can be is 9. Square root of 9, 3. So typically, if I'm trying to make something or see where something is as large as possible, I'm trying to make the thing I'm taking away as small as possible. And again, the smallest that can be is 0. Let's do another example. I feel like I see questions on your, or unless, I mean, but if there are questions, it's okay if there aren't, or if you just want to wait on for them a second. We can definitely do more examples. Question, right? Right, there's no number for the domain. The domain is kind of unpleasingly the set of all x and y that satisfy the equation x squared plus y squared less than or equal to 9. Let me show you another example that is similar to, that is similar to this kind of situation. Let's say our function was f of x comma y equal to the square root of 4 minus x squared plus the natural log of, let's go 25 minus y squared. Okay. So logarithms and square roots or even roots have kind of the same domain restriction with just a very small difference. So I know that for everything inside, and so I'm talking domain here, for everything inside the square root, I know that the insides of a square root have to be greater than or equal to 0. Totally fine for it to be 0. The square root of 0 is 0. On the other hand, for a logarithm, doesn't matter what the base is. For a logarithm, the insides or the argument has to be strictly greater than. We can't take the log of 0. We can't take the log of a negative. But the difference is one of these is a greater than or equal to inequality. The other one is a strictly greater than equality. It's just going to mean the difference between including the endpoints versus not including the endpoints. And let's solve these two different ways. So here's one way to solve this. Not my favorite way, but I'm going to do it. 4 bigger than or equal to x squared, or I would probably put the x squared on the other side and write it as x squared less than or equal to 4. And I don't love it, but I'm going to be taking the square root of both sides. So I have the square root of x squared less than or equal to the square root of 4. Square root of 4 is 2. And I know we've talked about this a little bit. What's the square root of x squared? Just x. The opposite value. Maybe I'm thinking of the other class. I'm thinking of my other class. Sometimes they're like, I think we talked about this. So the square root of x squared is the absolute value of x. Meaning what we really have here is that x needs to be smaller than 2, but it can't be too negative. Right? If x was -3, that wouldn't work. So we're stuck being between -2 and 2. Now, I'll say once again, not my favorite way to solve this. Here is my preferred way to solve an inequality like this. Instead of bringing y squared to one side and square root says, let's just factor the left-hand side. I'm going to factor this as 5 minus y times 5 plus y. Do be careful here. The order does matter. It is 5 minus y and 5 plus y, not y minus 5 and y plus 5. It's a slightly different thing, but it is specifically different. Because 5 minus y and y minus 5 are negatives of each other. So just in case you're curious, like what I'm saying is this factors this way, y squared minus 25 would factor as y minus 5 times y plus 5. And then I'm going to use the number line to determine where this thing is positive. So I'm going to put +5 on my number line and -5 on my number line. And I'm going to test points. Test a point bigger than 5, like 6. 5 minus 6 is negative. 5 plus 6 is positive. Negative times positive is negative. Similarly, pick something between -5 and 5, like 0. 5 minus 0 is positive. 5 plus 0 is positive. Positive times positive. Positive. Lastly, or alternatively, if you prefer, -5 comes from this 5 plus y. That factor has an odd power, so the sign changes. Or you can pick a point like -6, plug it in and see it's going to be 5 minus -6 is positive. 5 plus -6 is negative, and a positive times negative is negative. Josh.
Does that only work if you have the difference of squares?
No, it works for anything as long as you can factor it fully. So in fact, I'll show you another example in a little bit here that kind of goes on that. So here we end up getting, we don't want just the middle part here. We don't, right, well, we want where the whole thing is positive. I don't want the endpoints here because the endpoints make it equal to 0. So here what I'm getting for y is that y has to be between -5 and 5. It's not inclusive like the x one was. But it's the same sort of result. You're getting y or x to be in the middle of these two numbers. And you can solve it this way or that way. So then what's our domain? Well, x has to be this and y has to be this. We can't say it's like -2 to 2 and -5 to 5. We have to graph it. Well, we don't have to graph it. I like to graph it. So here's what the domain actually looks like in 2 dimensions. We said that x had to be between -2 and 2. And we are including that. Let me use a different color here. So when we're including something, we usually use a solid line to include it if we're having to draw it. So here's x between -2 and 2. And then y is between 5 and -5. But for y, we have to have a dashed line because we are not including the y is equal to 5. So we're having a dashed line there, an open circle. And same thing down here. We're going to have open circle, dashed line, open circle. We have everything in here. So the point like 1, 3 is definitely in the domain, or the point 2, 4 is in the domain, but 2, 5 is not. Even though x can be 2, y can't be 5. So here's our domain. And here's how we would write it. Not very pleasingly, it's really just write down all the x and y that satisfy the inequalities you've already written. So if I was going to write the domain, it'd be all the points x, y, such that x is between -2 and 2, and y is between -5 and 5. And kind of annoyingly, there's no better way of writing. This is the best thing we've got. Okay. Now here's where things get interesting. The range is harder to think about here. So when I think about the range, I try to be smart. Sometimes it works. I try to think about, well, if I say, for example, if I hold x or y constant, what can the other function do? So for example, if y were going to be 24, square root of 24. Basically, I want to make this part go away. So let's say we set y equal to the square root of 24. Why am I picking that? Because then the natural log of 25 minus the square root of 24 squared is the natural log of 1, which is 0. So if y is like way up here, well, x can only be, I don't actually get that big, right? If x can go as low as -2 as high as positive, I can only get as high as 2. That's not super helpful. So maybe from 0 to 2. Interesting. So the range for this function of the square root of 4 minus x squared is just 0. Sorry, I think I said -2 before. Is 0 to 2. Question, right? So that's an excellent question. I said I wanted to make this term go away for a minute. So I said if I let y be the number that makes the insides of this equal to 1, natural log of 1 is 0. Right, the square root of 24. So if y is the square root of 24, then I square it, I get 24. 25 minus 24 is 1, and the natural log of 1 is 0. But really, I was just trying to be like, if I just make this go away, like if I cover this up, what's this other piece doing? Well, it only goes from 0 to 2. Okay, so now the same sort of question here. If I make this go away for a moment, what's that doing? That's a harder question to answer. Well, of course, I'm running out of paper here. So we go down here. So if I set x equal to 2 for a moment, so that the square root of 4 minus x squared is 0, what's the natural log of 25 minus y squared going to do? Well, that's a good question. I could graph it. I don't really want to graph it though. I just want to think about it. So I'm always thinking about the biggest versus the smallest it can be. We probably could all answer What's the biggest this could be? Write down your best guess. Think about what you could let y equal to make all of this as big as possible. I'll give you 15 seconds. I'll remind you, we are subtracting off y squared. I'm really just saying, I'm letting x equal that so that the square root of 4 minus x squared is the square root of 4 minus 2 squared, which is 0. I'm just trying to like negate that for a moment so I can just focus on this. And the way I'm going to make this the biggest by making the thing I subtract off the smallest. What's the smallest y squared can be? 0, right? It's a really important thing to remember. So the biggest this can be is going to be the natural log of 25 minus 0, which is the natural log of 25. Not a very nice number, but it is a real number. Okay, here's a harder question to answer. What's the smallest this can be? Well, y can get really, really close to 5, but it can't actually be 5. And the reason it can't be 5 is if it were 5, 25 minus 25 is 0, and the natural log of 0 is undefined. But if we think about the natural log graph for a second, we can see that as the inputs get closer and closer and closer to 0, the outputs get more and more and more negative. So what really happens here is that this can be negative without bound. This function can go as negative as you want by letting y get closer and closer and closer and closer to 5. So smallest all the way down to negative infinity. Okay, so the range, kind of a wonky question to answer, but we can certainly go all the way down to negative infinity. And we can go all the way up to the highest values added together. It's kind of annoying. So we can get all the way up to when x is 0 and y is 0, we get 2 plus the natural log of 25. Not a great result, but it is a real result. Oh, you can't see that. Sorry, that's not great. That's our range. We're getting this highest value by letting x equal 0 and y equal to 0. Yeah, Josh. Yeah, so really, so the square root of 4 minus x squared. So honestly, what I was really doing is I was thinking about this previous problem. I was thinking about the fact that the square root of 9 minus x squared has a range that goes as low as 0 and as high as 3. Because the lowest it can ever be is 0 for a square root, and the highest it can be is at the apex right there, which is when x is 0 and 9 minus 0 is 3, or square root of 9 is 3. Same deal here, but I'm just saying the biggest this can be is when x is 0 and the square root of 4 minus 0 is 2. And the smallest this can never be is 0. Brian. I didn't define two ranges. I thought about the range of each individual part, and then I kind of added them together. Annoyingly, I don't love this question, but it is not an, it's maybe a little out there. I wouldn't say that. I would say I know that this piece of the function, independent of this piece, can go as low as negative infinity and as high as natural log of 25. And this other piece, independent of that, can go as low as 0 and as high as 2. So I can go all the way down to negative infinity plus 0, and all the way up to 2 plus natural log of 25. Kind of weird. I know it's maybe not the best one. I would say for this problem, we should probably not focus so much on the range, but definitely the domain here was something worth looking at. Sometimes we get kind of carried away if we're talking about the domain and the range. The range is less important, I would put that. Well, so what is it again? Let me look at another question. It might, I think, clarify some of the questions you have about what I've done here.
Yeah, but like, let's say the range is, one function is like -40, other range is -7.
So wait, when you say range, like the low end of the range, the high end of the
So
range,
The lowest end is negative.
huh?
That'd be a total range of -11.
Probably. As long as they're not as long as you're talking about just the Y's here and just the X's here,
Yeah.
then yeah, you can kind of do that thing. It becomes less, so yeah, let's look at another example, and I think it might offer some clarity. It might not, but I think it will. So let's look at this example. Let's say our function f of x comma y is the square root of y minus x over x minus 2. Where we don't really have the pieces separate from each other. This is more where what I was doing, I think, is useful-ish. Excuse me. Let's start with finding the domain, though. So right off the bat, before I do anything else, I know for sure that x can't be equal to what positive number? Right. X can't equal 2. In addition to that, we also have to say that the insides of that square root are greater than or equal to 0. Which I would probably rethink of as y greater than or equal to x. So what I'm going to do when I graph this domain, because I do like graphing the domain, is I'm going to graph the line y equal to x. Yeah, lovely. Before I do that, I'm going to be sure to exclude the line x equal to 2. So if I don't want to include something, I draw it as a dashed line or curve or whatever. So here we're excluding x equal to 2. And now I'm going to draw y equal to x, but I'm going to draw it solid because I want to include where y equals x, except maybe right there. I don't actually want just the line y equal to x. I want the region y being greater than or equal to x. So here's the nice thing about finding the region. If my domain is everything where y is greater than or equal to x, it's going to be everything that's on one side of this line. It's either on that side or that side. And the way we check is just picking a point on one side and seeing if it works. So if I, for example, pick the point 1, 0, is the point 1, 0 in the domain? Well, does it satisfy this inequality? Certainly not. 1, 0 is not in the domain because 0 is not greater than or equal to 1. Plugging in 0 for y and 1 for x. So that means that this side is the wrong side and this side is the right side. Everything on this side is in the domain. Except for the stuff right there. And again, writing the domain out, I would really just write the domain as the set containing all points x comma y such that y is greater than or equal to x and x is not equal to 2. There isn't a better way to do it. At least not, maybe there is. Maybe there is a better way to do it. No one's ever shown me a better way to do it. I don't really think there's a better way to do it, but I don't want to rule it out completely. Okay, let's talk about the range here. And here I think the method I used to find the range might make a little bit more sense. So I've got kind of all the stuff here. So here's what I would do. I'm going to fix x for a moment, because if I fix x, I can kind of see what's going to happen. So let's make a really smart choice and let's fix x equal to 3. And I picked 3 so that my denominator would be 1. So then f of 3 comma y is going to be the square root of y minus 3 over 1, which is the square root of y minus 3. And I know that y can be anything. Well, that's not true. Y has to be bigger than or equal to x, which makes sense. Y can't be 2 or 1 or 0 currently, because I've put x equal to 3 and y is bigger than or equal to x. But if y is any number bigger than or equal to 3, then my output can be 0 or any number larger than 0. So here so far, that means I get outputs from 0 to infinity. I can get anything that's non-negative if I let x equal positive 3. So right here, along this line, right here, this is where f of 3 comma 3 equals 0. And over here, f of 3 comma 4 equals the square root of 1, which is 1. And if I keep going up and up and up this way, my function values get larger and larger and larger because x stays as 3 and y gets bigger and bigger and bigger. The outputs get bigger and bigger and bigger. And then I can make a second smart choice. I'm going to fix, let me use red here. Now I'm going to fix x equal to 1, making the denominator negative 1. So then f of 1 comma y is equal to the square root of y minus 1 over negative 1. Or when you divide by negative 1, the same as multiply by negative 1, this is equal to the negative square root of y minus 1. So now as the y values get larger, well, if y is 1, I get 0. If y is 2, I get 2 minus 1, which is the square root of 1, but it's the negative square root of 1, which is negative 1. And the bigger y gets, the more negative my outputs get. So right here at 1 comma 1, I have f of 1 comma 1 is 0. And up here at say like 1 comma 2, f of 1 comma 2 is negative 1. And so on and so on and so on. So I can see that I get all the way as negative as I want to be as well. So I get everything from negative infinity to 0. And so I can see putting these two together, I'm getting everything, right? My range is all possible real numbers. So that's kind of how I might try attacking a problem like this to find the range. Because I'm not really sure what's happening. So I'm just going to say, well, if I let x do this, what happens to the function? If I let y do this, what happens? Most with a caveat. Most of the time when you have something fractional like this, you often are just getting everything. Because when you divide things by other things, you can often kind of make the denominator super small to make the fraction really big, or the denominator really big to make the fraction super small. And you can usually make it positive or negative, depending on if you make a good choice. I'm starting in on the line y equals x because that's the boundary, and then I'm just going up because I can't go down. I'm just picking the next integer. So I set x equal to 3, I picked the point 3,3, and then I picked the point 3,4, and then I would have picked the point 3 comma 5, which would have given me the square root of 2. And it really just kept going up and up and up. And I can see that if I just keep increasing the input for y, I'm going to increase the output every time. Excuse me. Let's see. No. Yeah.
I'm just confused because when you fixed it, I guess you do like that 3 comma y.
Right.
Ended up with 5 3 kind of. I'm just confused how you got the outputs of this.
So what I did was, right, here's my function. I'm literally plugging in 3 for x. So I'm getting y minus 3, square root of that, over 3 minus 2, which is 1. So that ends up equaling just the square root of y minus 3. And then I ask myself, okay, having set x equal to 3, if I let y range over all possible values it's allowed to be, what kind of outputs do I get? Well, y can go as low as 3, which gives me an output of 0, and y can go as high as infinity, which gives me an output of infinity. Same deal down here. If I plug in x equal to 1, I get the square root of y minus 1 over 1 minus 2, which ends up being the negative square root of y minus 1. If I let y be as low as possible, which is now as low as 1, 1 minus 1 is 0, square root of 0 is 0. And if I let y get infinitely large, I get the square root of infinity, which is infinitely large, but it's the negative of that. So it's really negatively infinitely large. I go all the way down to negative. If it helps, and I do encourage you all to sometimes maybe, I couldn't graph this on my own. I have no idea what this looks like in my head, but we could certainly use, if I can remember where I put it on my, why are you hiding from me? Sorry, I've hidden my graphs from myself here. I definitely think GeoGebra is worth your while to look at every once in a while. And let's see here. Takes a minute. No, I don't want my old graphs. So you either type in f of x, y, or probably just z equal to, what do we got here? The square root of y minus x. And then do a right arrow and then a divided by. And then we've got x minus 2 on the bottom. It looks super funky. Super duper extra funky. But one, you can see we are totally above the line y equals x in the xy plane. Right? We don't have anything on like in this half here. And also we get everything, right? This goes down, 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 down to negative infinity for our, right? The z values are the range. The z values go way, way down and way, way up. So you can kind of at least see somewhat that the range is looking like what we think it has. This is not the nicest of functions, but it still is this way. And if you zoom out, you can see it goes, yeah, farther up and far right. It keeps going. Oh wow, okay, but don't do that. Anyway, GeoGebra was kind of neat. It looks nice if you zoom out a little bit. Anyway, that might be helpful. It might be worth your time to do a little bit of exploring with GeoGebra and just kind of see if you've talked about or with like all the quadric surfaces we talked about on Monday. Maybe try graphing something to GeoGebra and switching a sign from a plus to a minus and seeing how it changes the hyperboloid of one sheet to a hyperboloid of two sheets. Or yeah, that's kind of the one real thing. Or just what is and in case you weren't here last time, don't call it what's it called, like a parabolic hyperboloid or something. It's a sap. Call it a sap. I mean, you can call it the other thing, but I never realized it was called that until I looked in the book the other day. I was like, oh, it's not a wrong name for it. It's just a battle. Okay, what else have I got here for you? For what time is it? Okay, let's look at a couple more examples. How about, this is a good one, yeah. Do I have a number? Number 4. How about the domain and range of something easier? G of xy equal to sine of x plus 3y. So when I'm thinking domain, the question I'm really asking is, are there any problems? When I say problems, what I specifically mean are division by 0, square root of a negative, or the logarithm of a negative or 0. But those are the 3 things in my brain. I'm like, okay, do I have any of those possibilities? Nope, nope, nope. Then I don't have any worries. So the range is, the domain is everything. Now, be careful. We don't get to say the domain is all real numbers, because our inputs aren't real numbers. Our inputs are coordinate pairs. So you could say the domain is either one way. If you want to say, you could say it's the entire XY plane. But the better way to say this is the set containing x comma y, such that x and y are anything. X is real and y is real. Or if you want to be extra fancy about it, you can call it R2. It's like the real number line squared. Usually people don't say R squared. The other people really say R2 is the correct way of saying it. So that's the domain here, our entire real plane. Not all real numbers, but all pairs of coordinate pairs of real. The range, on the other hand, is much easier to answer. We have a sine function. We have seen before that the biggest sine can ever be is 1, and the smallest sine can never be is -1. So the range here is very easy to answer. It is -1 to 1. I can definitely get it as big as 1 by letting y equals 0 and x equal pi over 2. And I can definitely get it to be as small as -1 by letting y equals 0 and x equals 3 pi over 2. For example, there are lots of other ways you can get those values. That's just one way. If you graph this in 3 dimensions, it kind of looks like waves going, like it looks like a plane of waves, like going this way, going that way. I mean, why am I trying to describe it when I can show you? Zoomed out too much. So if you zoomed out too much, you can fix that by maybe, no, it's right there. Hit the home button, like resets you. There you go. Oh yeah, super wavy. Kind of neat. Ooh, sometimes. Okay, anyway, that's useful. Yeah, right. Oh yeah, like if there was a 2 here, yes, then our range would be -2 to 2. Exactly. This number here is the amplitude of the sine function, and it definitely changes your range. And if you like added 1 or added 5, then the range would be -2 plus 5 to 2 plus 5. Yeah. Cool.